Today's lesson, section 9.4a, we're talking about vectors in 3 dimensions. So here, vectors in 3 dimensions are actually kind of the same or very similar to when vectors are in 2D. It's just that we're adding an extra component to our stuff for the z-axis. So vectors in space, which means 3D. If a vector, or vector A, has its component form of a sub 1, comma a sub 2, a sub 3, then that means a sub 1, a sub 2, and a sub 3 are components of vector A. Okay? Component form of a vector in space is represented by the initial point and the terminal point, where you take the terminal point's values minus the initial point's values to get the vector. So it's direction, okay? Just like you would in 3D space. It's just that there's an extra one at the end, okay? So like, for example, 1A here, they give you the initial point, the terminal point. They want you to find the components of vector A. So that means that A will be 3 minus 1, and then 1 minus a negative 4, and then negative 1 minus 5. Okay? So when I actually subtract those, 3 minus 1 is 2, 1 minus a negative 4 means plus, so I get 5, and negative 1 minus 5 is negative 6. So then that would be the vector for A. If a vector has the component form of negative 2, 1, 3 for vector B, and has an initial point of 2, 1, negative 1, then if we want to find the terminal point, then usually you would take the subtraction. So vector B is this. Okay? That's supposed to equal your terminal points minus each other. So x2 minus 2, comma y2 minus 1, comma z2 minus a negative 1. Okay? And now you can kind of set up equations to solve for these. So x sub 2 minus 2 equals negative 2. Y sub 2 minus 1 equals 1. Z sub 2 plus 1 equals 3. Okay? And we can solve. So if I add 2, I add 1, and I subtract 1, that gets me values of 0, 2, and 2. So my terminal point, we could say Q here, so 0, 2, 2. And that would be my answer. Okay? Now, magnitude for a vector is very similar for 3 dimensions. We take the magnitude of a vector A. Looks like I have a plus sign where I shouldn't. Let's make that a comma. So a sub 1, comma a sub 2, comma a sub 3. We take all of those numbers squared and add them together, and then take the square root of them, kind of like you would in the distance formula, in the magnitude formula that we've already used for our stuff. Okay, so let's do some examples of this. So the magnitude of this vector u, so 3 squared plus 2 squared plus 5 squared, gives me 9 plus 4 plus 25. So 9 plus 4 is 13. Plus 25 is going to be 38. And that does not reduce because it's 2 and 19. So my magnitude for vector u is square root of 38. Same thing for vector b. I can take 0 squared plus 3 squared plus a negative 1 squared. That gets me 0 plus 9 plus 1, which gives me the square root of 10, and that does not reduce as well. Okay, so magnitude is very similar to what we've already done before in 2D. Okay, here we have algebraic operations on vectors in 3D, so the same kind of things apply if you have two vectors like they do in 2D. It's just that you have that extra component at the end. So if I'm adding my vectors, I just add each component, like that's like components. So the x's go together, the y's go together, and the z's go together, and you add them. Okay, if you're subtracting, then you subtract the x's, you subtract the y's, and you subtract the z's. If it's a scalar, like a number like c times a vector, then it's like distributive property. So you're multiplying that scalar to all three components inside the vector. Okay, so here, for example 3, they gave you two vectors, and they want you to do the following operations, where you add the two, you subtract the two, and then you're multiplying them by certain numbers like 5 to vector u, and then we take -3 times vector v. Okay, so let's do them all. So if I'm adding, that means 1 plus 6, and then -2 plus -1, comma 4 plus 1. So then 1 plus 6 gives me 7, and then -2 plus -1 is -3, comma 4 plus 1 is 5. Okay, so now let's subtract our vectors. So I do the same thing, 1 minus 6, -2 minus a -1, and 4 minus 1. So 1 minus 6 gives me -5, -2 minus a negative means plus, so then I take -1. -2 plus 1 gives me -1. Then 4 minus 1 is 3. And so then that would be my new vector when you subtract them. So then now if we put some scalars in there, okay, so here, let's write this out a little bit more. Okay, so distribute, so that makes it 5, comma -10, comma 20, and then let's make that a plus and multiply it all the way through, so -18, comma 3, comma -3. Okay, and then let's add, so 5 plus -18, -10 plus 3, and then 20 plus -3. So that gives me -13, -7, and 17. And so then that would be my new vector for that one. Okay? Next thing is, just like in 2D, we can express our vectors in ijk form. Okay, so instead of just ij, now that you have that z value, k is going to represent the z value for this. So if I have a vector a sub 1, a sub 2, and a sub 3, then to express it in terms of I, j, and k, that just means that I take ai, or a sub I times I, or sorry, a sub 1 times I, plus a sub 2 times j, plus a sub 3 times k. And then that would be my ijk form. Okay? Pretty simple. Here, now, just like in 2D, we can take the dot product of two vectors in 3D. So if you have two vectors, then the dot product, or vector A, or dot product of vector B, then that means, remember, that dot product is like a scalar in the end, so it's just one number. So you multiply your x components, so a sub 1 times b sub 1, and then you multiply your y components, and then your z components, and then you add them all together, just like we do in 2D. Okay? So here I have some dot products to do. So for this one, -1 would be multiplied by 6, plus 2 times 5, plus 3 times -1. And so then -6 plus 10 minus 3 will get me 1. Okay? And that would be the dot product of those two vectors. Same thing works in ijk form. So remember, ijk's get dropped. You're not worried about them. So 2 times negative 1 plus 3 times 2 plus negative 1 times 8. So then now, 2 times negative 1 gives me negative 2, and then I get a 6, and then I get a negative 8. And so then that gives me, oh, and it looks like my picture's a little off from my thing. This should be negative, so I apologize for that. So this one should be negative, so then 6 should be negative. So they're all negative, so that means you get a negative 16 for your dot product, okay? And then the last thing we'll talk about in this section is that you can find the angle in between two vectors, where if we let vector u and vector v be vectors in space, and theta be the angle in between them, then cosine of theta equals the vector of u and the dot product of vector v divided by the magnitudes of vector u times vector v. Okay? Now, one thing to remember is that in particular, if vector u and vector v are perpendicular, another word that we'll use is orthogonal, or orthogonal. Okay? If and only if their dot product is 0. Okay? One of the nice things about this. So basically, if they're perpendicular, your dot product's 0. Okay? And then vice versa. So if it's 0, then they're perpendicular. So example 5 says, show that the vector u, 2i plus 2j minus k, is perpendicular to 5i minus 4j plus 2k. So that means that using this formula, or actually this part, so if I use the dot product here, and I take the dot product of them, and I get 0, then they must be perpendicular. So 2 times 5 plus 2 times negative 4 plus negative 1 times 2. So it gives me 10 minus 8 minus 2, which negative 8, negative 2 are negative 10. So 10 minus 10 is 0. So that means that u is perpendicular to v. Okay? Have fun.